All right, so we're going to look at logistic functions, which are similar to exponential functions for part of the graph, but not the entire graph. So a logistic function is used typically when we talk about population growth. Population can grow exponentially, but then it only lasts till a certain value or till a certain point. It's really not unrestricted like we did talk about yesterday. So really what happens is if your population is going to grow, eventually it has a limit how far it can grow. Either the land may not be able to sustain the population, or starvation or disease from being overpopulated will start to kick in, and then your growth will start to slow down then. And that's the way a logistic function is going to be shaped then. So a logistic function in this form, sometimes your base, instead of being a value like b, it would be a value with a base of e, that number that's about 2.718 that we talked about a little bit yesterday. So you have something in the numerator there, and then 1 plus that product in the denominator that has the exponential piece to it. And the limit for the growth is going to be whatever this numerator is. And we talked about that before when we talked about carrying capacity. I think we had a bear problem or deer or something like that. So that's what that numerator is going to give you. So we can put these in the calculator, and you see the basic function for your logistic function here. And if you look at that graph, you can see that this is 1 over 1 plus e to the negative x, it looks like in there. And what's going to happen is your domain is all reals. The range is from -1 to 1. What you don't see on your graph here is we have asymptotes, horizontal asymptotes that trap this or bound this graph here. So y equals 0 and y equals 1 are both horizontal asymptotes. The population is never actually going to equal 0, or whatever this happens to represent, and it's never going to go above that upper bound there, which is 1. It's a continuous graph, so any x value that you pick, you'll be able to get a y value. It continues to increase from -infinity to infinity. This symmetry we can talk about. It's not an odd function, it's not an even function, but they're going to talk about this point right here. Is a point of symmetry, kind of like we did with the origin. If you turn that on that particular fixed point, it looks the same upside down and right side up, using that as your fixed point as opposed to your origin. Bounded above and below, we talked about the asymptotes, so that boundedness is different from exponential graphs. Those are also the horizontal asymptotes. We have no vertical asymptotes. There's no vertical line that this graph gets close to. And then the last piece is your end behavior. The first part talks about the left tail. The left tail is going to get close to this lower horizontal asymptote, which is at 0. And then the right tail is getting closer and closer to this horizontal asymptote of 1. So those are the pieces that we looked at with exponential functions as well. So you can find this point of symmetry, this green point up here. This one's kind of deceiving because this one is right on the y-axis, but that symmetry point doesn't have to be right on that y-axis there. It may be somewhere else. And what this is telling you is that the y-coordinate for that value is always going to be whatever the numerator is. That's that c value divided by 2. So it's halfway between the two asymptotes there. So wherever your graph is halfway between the asymptotes would be that fixed point. We don't really talk a whole lot about symmetry at these. When we talk symmetry, we talk about x-axis symmetry, y-axis symmetry, the origin. Those are the 3 big ones. So let's try and graph some of these with the calculator here. So this example 6, we're going to look at a logistic function. And to put this in your calculator, you have to be careful. We need some parentheses with this. So if I flip this backwards here. There we go. So if I put this in the calculator, the 8's in the top. It's the only term in the top, so I don't really need parentheses around it. But the denominator, I definitely need parentheses around. 1 plus 3 times, and I'm going to put the 0.7 to the x in parentheses as well. So that base, raised to that exponent, let's try it again. There we go. Inside those parentheses, and then I also need another set of parentheses that close off that denominator. So 1 plus 3 times the 0.7 raised to the x. So order of operations, my calculator should take my values for x, 0.7, raise it to that value, take that outcome and multiply it by 3, take that outcome, add the 1 to it, and then finally 8 divided by that outcome is what my calculator should be doing for me. All right, so we're going to go through and graph this. Now, if you look at this, we said that this number up top here is going to be my my upper bound. It's my horizontal asymptote. So I should have horizontal asymptotes at y equals 0. They all start with y equals 0. And then also y equals that c value, which is 8. So y equals 8 should be my other horizontal asymptote. They also talk about the x or the y-intercept. Your y-intercept, if in this equation you let x equal 0, we would have 8 in the top. We'd have 1 plus 3 times 0.7 raised to the 0 power. And yesterday we talked about anything raised to the 0 power is going to be 1. So I have 1 plus 3 times 1, which is going to be 8 over 4, which is 2. So my y-intercept is when x is 0, my y value is 2. So let's look at the graph of this. I need to reset my window to something that makes sense for this graph here. So my x values, I'm not sure what they're going to range from and to, but our x values can be anything we want. So maybe we'll go negative 10 to 10 and see what the graph looks like. And then my y values, my horizontal asymptotes are at 0 and 8. So if I start at negative 1, which would be just below the horizontal asymptote, and go up to 9, one above that asymptote, I should be able to see the entire graph then. Let's sketch this graph here and see what it looks like. And it looks pretty good. You can see that we're going to have horizontal asymptotes above and below. Calibration's pretty screwed up today. And you can see that my transition point, or that symmetry point that they were talking about, would be c divided by 2, which would be at 4. So when the height, 1, 2, 3, 4, is at 4, that green point, the second one there, is the point of symmetry. If you need to find that. I don't know that that would be something that I would bother to ask for, because we will talk about that in calculus in terms of not symmetry, but a change in concavity, a change in the shape of the graph there. All right, so let's look at this next one here, see if this will cooperate with me a little bit. So this one, same idea here. Again, without the graph, I can go through and sketch most of this even without the calculator here. My y-intercept, if x is equal to 0, I would have 20 over 1 plus 2 times e to the negative 3 times 0 would be 0. Don't worry that you have a value of e there, because we're raising e to the 0 power, which makes that 1. And I have 20 over 3 for that y-intercept. About 6 2/3, 6.67. And then horizontal asymptotes would be where that numerator is, the value for the numerator there, which is 20. So I'm going to have a horizontal asymptote at 0. Horizontal asymptote, I'm going to say this is 20 up here. Right? And then at 20/3, 6 and a little bit there, I'm going to have that y-intercept, so about there. And then if I sketch this curve, that transition point is going to happen when y is halfway between the asymptotes, so at 10. So right about there. So if I sketch this curve, oh my gosh. I'm going to try this one more time. I don't know why this board is not cooperating today, but let's try it again. All right. So y-intercept and then that transition point halfway between the two there. All right, so you can go through and sketch these. You don't have to plot a lot of points, just the y-intercept, the asymptotes, and that shape of that graph is going to follow that same pattern there. All right, so you can find equations using your calculator. So a population model is what we'll come up with. This first one is exponential, not logistic like we just did, so like we did yesterday. When is the population going to surpass 1 million people? And they gave us 2 data points. So let's put it in the calculator. You can clear out whatever you have in here for now. We're going to go into stat because I want to put, I have 2 data points and I have no idea what this equation is going to be. So let's put this in. I have, let's see, when the year is 2000, so let's call the year let's let 0 equal the year 2000. And typically that's what they'll have you do. And the year 2007, we'll let that be 7. And then my y values that correspond with that, so I can slide this enough that I can see it. 898, 670, 898, 769. Make sure I got it. Oh, it's 59. Right, and then the second one there is 939, 899. All right, I think I got it now. Yes. All right. So when we have that, they want us to come up with an exponential function. So you can get out of that window, and we're going to go into stat again. And go over to calculate, and then we want exponential regression. So you can arrow down or you can arrow up. It's pretty close to the bottom there. So for me it's 0, exp reg. So that's what you're looking for. And for me it's 0. So that's what I want. And then again, depending on which operating system you have, it'll either say just this exp reg, and you can put the equation right next to it, or if you have my operating system here, you have to actually number down to where it says store reg equation. And then whichever one you have, at this point, if you didn't have to arrow down, you just type this in. We can hit the vars button, go over to yvars. It's a function, and we can put that right into y1. Right, and then everybody hit enter twice, and it'll go through and come up with that value for you. Right, so we came up with the equation. The equation's y equals ab to the x exponential. The value for a, yesterday we talked about that. That was the initial value. That was that 898, 759. And then the b value, now you're going to need to use at least 3 decimal places. And as these numbers get really large and really small, even more than that is even better. So 1.006 if I round that to the x. So there's my equation. And then the question for this is, when is their population going to exceed 1 million people? So if we go into the second and the table function, if you type values in for x for time, well, t equals 0 is 2000. So if I type in 15, that's 2015. You can see your y values at 989, so we're not quite there yet. So let's go higher. Let's go up to 20. So 2020. Now you can see, now this flipped it over into scientific notation, 1.02 e to the 6. If you arrow over on top of that number, down the bottom there, it'll give you the expanded. So we're above 1 million at that point. So somewhere between 2015 and 2020, we're going to exceed 1 million. So let's get closer. Let's try 18. So 18, you can see we're still above 1 million. 17, 1E6. So that's going to be one with, the 6 zeros after there. So it's going to be over 1 million at that point. Let's see what happens at 2016, see if we're there. So 2016, you can see it's just below. So for this one, in the year 2016, their population will exceed 1 million. And that's what you can do for something like that, given a couple of data points there. All right, no idea what I just did for that. Here we go. All right, and then the last one on here, same idea, but now we're looking at a population model, and this one is logistic. So we'll put this one in the calculator. And then when is this going to exceed 1 million? So same idea. Just going to slide this one over a little bit. So same idea. Now, again, with these logistic models, you have to be real careful typing this in. It's real easy to miss parentheses that you actually need. So for this one, that numerator, you can put parentheses around it or not because it's one single value there. 1,301,642 divided by, denominator definitely needs parentheses around the outside part, so 1 plus 21.602, and then that's times E. So E, you do the second key and the ln button, which is right next to 4. You can see in blue it says e to the x. There we go, E, and then my exponent was negative 0.05. 0.054, and then x was my exponent. I can't get a t for my exponent there. All right, parentheses around the whole thing there. Just check you real quick, make sure that all your values are typed in there correctly. All right, and we could go through and graph this, but just be careful. Remember this upper value here, that is your horizontal asymptote on top. My bottom horizontal asymptote will be at 0, so that's a pretty darn big number. If you want to put it in your calculator, you got to make that window really big. I'm not going to bother to graph it. I'm going to do just like I did for the last problem and look at my table of values. Right, and I'm looking to see when does the population exceed 1 million. And they said for this one, T is the year after. So 1900, years after 1900. So T equals 0 is my 1900. So if I type in T is, I don't know, 75, that's going to be 1975. So I'm going to typing in there. So let's try some values there. So 75. Now it's getting me closer to 1 million. I'm up to 874,000. So let's go higher than that. Let's try 1980. That's closer, so it's bigger than 1980. Let's try 1990. All right, so 1990, we're over 1 million, so it's got to be somewhere in between there. I'm going to go to 85. 85 is a little over. 84 is a little under, so 1985 is when the population will exceed 1 million. I should say this too. If you can't type values in, to your calculator like we're doing, hit the second key and the table set key, which is the window button, and make sure independent has ask highlighted. Don't worry about what table start or delta table are. We don't need that. Just ask for the first one, auto for the second one. You should be able to type values in. All right, that's it. So you have the homework problems to do over the weekend, and you're good. It's not recording.